So we want to start out looking at item number 11. You're going to notice as we start getting farther along, and this is the way it's going to be in industry, you're going to see that we're going to start adding parts to it. I guess if we really wanted to be technical about it, we could have an assembly drawing that showed this 1-inch length gets face down some during the lathe operations, but we just communicate that to you, and that's not a terribly important feature. If you look at this part, the only thing that we have left to do on it is to machine this flat on there. So you should know already what kind of tool we're going to be using to machine that flat on. It's definitely not a drill bit, right? Because a drill bit has a point on it and it doesn't machine side to side. We're going to use an end mill. So we have to come up with the appropriate size end mill. Well, the width of that slot, and that slot is strictly just a flat for your set screw on your flywheel to set down on. When you put the flat down, or when you put the set screw down on, it's going to distort the material, and if we pushed it right down on the round stock, it'd be hard to get your flywheel back off. So we do that for a very important reason. The width of that slot is 190 thousandths. We would have to have special end mills ground up to find one that measures 190 thousandths. But if I go to my decimal equivalent chart, and the decimal equivalent chart gives me all the different sizes for fractions that I want to work with, and I start going down through here, there's a fractional size that's very close to 190 thousandths. That fractional size is so close, it's only 2.5 thousandths difference, but if I go back and I look at the 190 thousandths dimension, the 190 thousandths dimension is called out as 0.19, so that's a two-place decimal. If I go down to the bottom of my drawing, and I don't have it sketched out here, but you should know where your tolerance block is. Two-place decimals have a plus or minus 10 thousandths tolerance. So I could be as small as 180 and as big as 200, and it'd still be an acceptable part. Well, 187.5 thousandths for a 3/16 end mill is an appropriate size. It fits inside that window, so that's what we're going to use. Okay? Now, it might be difficult for you to start thinking about, but how are we going to hold on to a piece of round stock? Well, the round stock needs to be held onto in such a way that this is a precision surface. I didn't draw it up here, but your tolerance is a very tight tolerance on that 3/16 diameter, and it's a ground dimension, because when we buy miles and miles and miles of that material, it's precision ground, and it's within a couple of tenths of a thousandths, okay? A couple of tenths of a thousandths, so way smaller than a thousandths of an inch. If I hold on to it and I'm pushing the vise, put pressure on the two tangent sides, I'm going to put flats on it. Well, now if I have a crankshaft that's got flats on it, it's not going to run real well, right? You wouldn't take your small block Chevy engine out of your car, take the crankshaft out, and beat it with a hammer and put it back in and expect that it's going to run the same. We're not going to do the same thing with this. So we're going to hold on to it with a precision tool. This is a different tool, or a variation of the same tool that you've had experience with. The tool that goes inside the spindle that clamps onto your end mill is called a collet. A standard collet size is called an R8 collet. R8 is just a standard that's set up that says this size, this shape, with this thread in the back side is called an R8. It's got all different size holes in it, so it'll hold different diameters. Well, there's a different style collet that's mainly used on lathes, but we do use it to hold round stock in mills, It's called a 5C collet. Again, that's a standard that says a 5C collet. It's this diameter, this taper, this length's got a thread on the end of it. I'm satisfied, right? What's important when I pick a size of a collet? That if I'm holding on to a 3/16 diameter, I have to make sure that I've got a 3/16 diameter collet, right? Because collets, most collets that we use on this end of the shop, need to match their diameters. If they don't, you're going to overflex the collet and cause it to be distorted. Once it gets distorted, it can cause problems, and yes, it can be a safety issue, okay? So we've got a collet that's going to grab over this end and hold on to the entire length of the workpiece, right? It'll support all this material just by holding on to the back end. Now, if you've been in my classes, you understand that one of the worst things that you can do is machine into one of my collets. So that collet, again, is round, and there's a block that goes over top of it. You're going to see all that when we get to the shop. So you just want to think about a collet holding on to this end. Well, because you don't want to machine into the face of Mr. Bryant's collet, what do I want to make sure of? I want to make sure that I have 520 thousandths plus 190 sticking out of the face of the collet, right? So the collet looks something like this. It's tapered back here. And it's in this square block. That square block allows us to hold it in a vise, okay? So we've got this collet. I need 520 plus 190, that's 620, 710. Well, because you don't want to machine into one of Mr. Bryan's collets, we want some extra clearance in there, right? But because there's such a short distance here, I want to hold on to as much as possible. So if we have roughly 3/4 of an inch sticking out, or 750 thousandths, we should be in good shape. So now all this kind of sitting out there in space, but the shaft is stiff enough to handle our positioning technique, okay? So now we've got this mounted in the machine, and you're going to learn more about this when we get down to the machine, but the whiteboard demonstration for this is relatively straightforward, okay? There's two simple ways that I can find where that slot is. I've got the dimensions, the dimension to the leading edge, I've got the width of it, but what do I care about? What I truly care about is the distance to the center of that slot. So that's 520 thousandths plus half of this, which is 95 thousandths, which gives us 615 thousandths. So I'm going to write that down here, 615. That's an important number, right? We've already said that we're going to use a 3/16 end mill, so there's two techniques that I can use, okay? The first technique we're very comfortable with. We can put our edge finder in the machine, and just so you don't have to crank the table up and down, what you can do is put that 3/8 edge finder straight into a 3/8 collet. So now I don't have to crank the table up and down to get to my workpiece, okay? So we can put an edge finder in. If I come in and I edge find, again, there's my 200 thousandths diameter edge finder, right? Come in, I edge find, it kicks off. Set my dial to 0, and this is the x-axis that we're working with. Set my dial to 0. So I'm going to say set dial to 0, edge find. You should take for granted and assume that you set 0. Right? Once I set my 0, how far do I want to move over? Well, the next step is to move over in the same direction 100 thousandths. 100 thousandths move. Now what's that for? That's for the radius of my edge finder. Okay? What's my next step? I'm going to move over 520 plus half of 190. We've already said what it is. We're going to move over an additional 615 thousandths move. Now, you have to ask yourself, do I want to edge find going in this direction? No. Once the mill starts moving, I'm just going to move back and forth. I don't care where the center of the part is. And I can visually see that. So now I'm going to switch over to my 3/16 end mill. Right? We got to calculate our RPM. 4 times 100, which is our cutting speed. Well, actually, let me back up a second. This is actually tool steel, annealed tool steel. It's not mild steel anymore. It's 4 times the cutting speed of tool steel, which is 50. So it's 4 times 50, which is 200, divided by my diameter, right? And I'm going to round my diameter instead of 187 and a half to 0.2. It allows it to be easy for me to calculate. So 200 divided by 0.2 is 1,000 RPM. So we're going to change the belts so that we're running as close to 1,000 RPM. If my machine doesn't have an exact 1,000 RPM setting, where do I want to be? I would much rather be slower than my calculated so that I don't run into any heat problems, because heat in tool steel causes heat treatment if it gets too high. We don't want to make it very hard. We just want to machine that slot in. So 1,000 RPM. Okay. Now we're going to come down and I'm going to color. I'm going to take my Sharpie and I'm going to color that surface. Okay? We're actually down here, but I don't want to color over what I care about. So we're going to come down until it just touches. Okay? Lock your x-axis in because the movement of the table may get away from you. Okay? Likely not, but I'd rather be safe than sorry. So we're going to lock our x-axis. Here, come down and touch the top surface of the part. Set my dial on my knee, which is that big crank, to 0. Once we set it to 0, because these are pretty stiff machines, you potentially could take all 30 thousandths at one time. But I would prefer you to take it in 2 passes. So we're going to move up. Once the end mill is moving off to the side or spinning off to the side, we're going to move up 15 thousandths, put some cutting oil on it, take our y-axis and feed across. Don't have to worry about climbing conventional milling because we're going straight through the part. I get equal forces on both sides. The rotation wants to drive it one direction, but I don't have to worry about climb or conventional. Okay? So now we're going to dial it up another 15 thousandths to come to our 30, and we're going to feed back through. Again, make sure you got cutting oil on there. Once you get that done, you can take this whole assembly off, deburr over the top. I like taking a file over it while it's on the machine, and then you can take some emery cloth, and as long as it fits, as long as the outside diameter is going to fit inside your flywheel, that's all you really care about. Okay? That part's finished. Well, let's back up. So what I did is I walked you through how to locate using an edge finder. That might be your easiest way. There's another technique. Avoid the edge finder completely, right? Avoid the edge finder, come down here, put your 3/16 end mill in. So my 3/16 end mill is sitting right here, and it's rotating in such a way Clockwise rotation, right? Normal rotation clockwise from the motor end. I'm going to get over here with my hand wheel. I'm going to feed in. I'm going to take a strip of paper, put it between the end mill and the face of the part. I'm just going to lightly hold on to the paper. And you can have the paper several inches long. 1,000 RPM, and I'm going to feed nice and slow, have the paper between the part and the end mill, and come in nice and slow until the end mill pulls the paper out of your hand. What that means is that you have lightly pinched the paper between the end mill and the part. That gets you within 3/1000ths easily. Well, I've got plus or minus 10, plus or minus another 10. So I can be as much as 20/1000ths off in either direction. That's a pretty generous tolerance there. Once I touch off with that end mill, not even touch off, just drag that paper, we call it the paper trick, okay? You're within 3/1000ths, release the quill up and let it get up and out of the way. And now you're going to move over so that the edge of your end mill matches the edge over here. So we're not moving 615 anymore. We're moving 520 plus 190, which is 710/1000ths. I don't have to change any tools. I don't have to take the edge finder out. I'm ready to start cutting. Okay? Now I'm going to color the top surface of the part, bring the end mill up while it's rotating, 1,000 RPM, till the black Sharpie goes away, set my dial to 0, back off, 15/1000ths, feed across, another 15, feed across, part's done. Deburr it, take it out, set it in your toolbox, it's ready for assembly. Okay? You can double check with inspection, make sure it fits inside of your flywheel. But aside from that inspection, as long as it goes in and you've got that nice flat on there, you can take your calipers and measure 520, make sure it fits inside your flywheel, part's complete. Now we're going to move on to our piston. Now we're getting into item number 6, which is our piston. And we're rolling right along on finishing these parts up. We just finished up our crankshaft ready for assembly. Today we're going to get finished up on our piston. It'll be ready for assembly when we get out of here today. The only thing that we've done to this component so far is we've faced it to length and we've lightly deburred the corners. Now the first thing I want to look at on this component is the tolerance stack up. You're going to hear those terms pretty regularly as you move forward in your engineering experience. But there's a lot of these numbers, the 930, the tolerances or the dimensions, 930, 310, that's plus or minus 10. So if I start thinking about, well, if I hold one really heavy on the plus side and I cut the other one really light on the minus side, those tolerances start stacking up. And it's difficult to see whether you're going to run into out of tolerance issues when you're finished your part. Because these are kind of a different animal. The only people that it has to please is your professor, your teacher that's teaching you how to do this, yourself, and ultimately that the air engine runs. We can cut and hack and do a lot of things to make this thing lighter and whatever, but as long as it runs by the end of this lab, that's really what we care about, okay? But if you were going to do this as a component that you were going to sell to a customer, and there were features that were out of tolerance, what does that mean? That mainly means that you don't get paid, because this drawing is your contract, okay? So if you don't make parts to your drawing, or you don't do your job to your contract, you don't have to get paid. That's really what's important when you get out into the industry. You want to make sure that you're getting paid, and the best way to do that is make sure your boss is getting paid, okay? So if you look at your drawing, first and foremost, there are two dimensions that are labeled with X and Y. Now why would that be? Because this 813 is a 3-place decimal, right? There's 3 spots after the decimal point. So that means that's a plus or minus 5 thousandths tolerance. If I assume that the part is 930 and I subtract 813 from it, I get one number for X. But if I measure it, the reality is that I cut this part at 939. Now 939 on a caliper reading, is it still a good part? Absolutely, it's within the plus or minus 10 thousandths tolerance. But if I did the math as though everything were perfect, right, they were exactly the dimensions, then this dimension would no way allow this 813, which is the critical dimension, top of the piston, center of the pin. Everything down here doesn't matter. Where it does matter is how we're going to do the machine work. Okay? What I have sketched up over here is a drawing. This is our component. And on the first part of this lab, we learned about a collet called a 5C collet. And then this block that holds the outside of the collet and allows it to be compressed. This square block actually allows us to put it in a vise, right? But I've got this drawn up here for a very good reason. The first time that I clamp this part in, because you don't want to cut into Mr. Bryan's collets, we need to know how big this Y dimension is, right? How's the best way to do that? Well, if I take 930 minus 310, that comes up with a value, right? Well, it does, but it's not an accurate value because your part may not be 930 thousandths. So what I'm going to do is I'm going to erase 930 and I'm going to say my dimension. So you're going to take your part drawing when you're making this part and you're going to scratch out 930 and you're going to write in what your actual dimension is. Now, if I take my dimension and I subtract 813, it gives me a dimension here, right? For the X. If I take my dimension, subtract 310, now I can fill in for Y. Well, it's critical for Y right now because the end of the piston that gets the flat machined on it's going to be sticking out of my collet. So ultimately what I want this to look like is I want there to be a step here. Okay? All that material here is going to go away. And we have to hold that tolerance. We have to hold the dimension in 2 directions for that step. Lastly, we're going to put the hole in it. Different issue right now. We're not there yet. So the first thing I need to do before I even clamp the workpiece inside the collet, I have to calculate what my Y dimension is. So let's just assume that my part is exactly 930 thousandths. So I'm going to put in 0.93. I didn't even have to scratch that out for mine because I'm that good, right? So 930 thousandths minus 310 gives me 620 thousandths. So now that I have that dimension, the distance from the face of the collet to the end of the part has to be 6.3 plus. I'd like it to be somewhere in the neighborhood of like 680. I'd like enough sticking out that there's no way possible that you're going to run into my collet. Okay? So I'm just going to say I want that at 680 somewhere. And you can use your calipers to take a measurement once you have it clamped in. And you can really lock it in with a spanner wrench. You'll learn what that is. It's not going to go anywhere. Okay? Let's go ahead and place it in the machine after we get it locked down. The first operation that we're going to do is machine that flat. So the flat is going to come back, what? 930 minus 310, 620 thousandths. Okay? So we're going to machine back 620 thousandths. Let's go ahead and take this guy off there. What kind of a tool are we going to use to machine that flat on? We're going to use an end mill. I would like the end mill to be wide enough that it will cut the entire width of that flat at one time. Now this piston is 1/4 of an inch in diameter. A 1/4 inch end mill will do the job, but it's definitely more work for you. So you have a 5/16, a 3/8, and a 1/2 inch in your toolbox. I'm going to prefer to use the 3/8. It's just what I've always used. Okay? So your 3/8 end mill is going to be sitting up here like this, right? And your flutes come up around like so. Now we have to reference that end mill so we cut an accurate part. How's the best way to touch the end of that component? Well, once you get some experience, what you can do is color the end of the part, color the top surface of the part with your Sharpie, start the spindle, have to know how fast to run it, right? So we're going to say, number 1, I'm going to say 3/8 end mill. Right? What's the material? Annealed tool steel. So that's a cutting speed of 50. So 4 times 50 is 200. Divided by 0.4, right? That gives me an RPM of 500 RPM. So we're going to run a spindle speed of 500. Okay? Speed of 500. We're going to start the machine up. Again, if I colored the end, I can bring the axis in until I just see the Sharpie go away. And because it's a tool steel, the cutting forces are heavy enough, normally you can hear it cutting. But until you get some practice, I would say let's go for the paper trick. Okay? We're going to take our piece of paper and kind of have it float inside that gap between the end mill and the end of the part. I'm going to feed my axis in until it just pulls the paper out of my hand. Okay? Once it pulls the paper out of my hand, how close am I? Well, I'm within 3/1000ths because that's what the thickness of a sheet of paper is. So at this point, to touch off. So I'm going to touch off the end of the part, okay? So now we're ready to start thinking about machining back the length. The best way to machine back the length is to know where the top surface is, because that's where the depth of that little step references from. 75 thousandths plus 5 minus nothing. Pretty tight tolerance again. So we're going to bring the tool up and bring it over the top of the part. Start the spindle, and you're going to bring the knee up. That's that big crank. Bring the knee up. Make sure that the quill's locked in. Bring the knee up until you just see that Sharpie start to go away. Once you see it, set your dial to 0. When I touched off the end, I should have set my dial to 0. Okay? So now we've got our 2 references set up. If you're like me and you forgot to set your dial to 0, go back and reset it to 0. Okay? You have to do your touch off again, or your paper trick. Once you do that, set your dial to 0. I need to know how far back I'm going to run. Well, shoot. I don't remember. Well, I wrote down my dimension on my drawing. 930 minus 310 is 620 thousandths. we're going to feed ultimately 75 thousandths deep. Let's take it in 3 passes, okay? The first pass I'm going to take is I'm going to bring my knee up 30 thousandths. Start my spindle. When the end of the tool starts to touch, my dial should be set to 0, right? As soon as I hit 0, I'm going to go 600 thousandths. 600 even. Okay? What that does is gets me within 20 thousandths of that end. So we're going to feed in. So number 3, Z minus 30 thousandths. Then we're going to say X 0.6. Good enough? Now we're going to feed back off the part. And we're going to go Z minus 30 thousandths again. So that's going to take us to 60 thousandths. That should get us within 15 thousandths of nominal on this dimension. What's our next step? X 0.6. I've got most of the material gone, okay? At this point, I'm going to stop the spindle. I'm going to back the end mill far enough away that I have some room to work. And I'm going to blow all the chips off, make sure I don't have any chips in there. I'm going to take my calipers the best I can, and I'm going to measure that thickness. Because even though the dimension here is from the top surface to the flat, the easiest dimension for us to measure is going to be this one. The thickness from the cylinder side to the flat. Well, what does that need to measure? It's 250 thousandths diameter minus 75. That's 175 thousandths. Well, if I take this plus 5 minus nothing, now that I'm measuring this, it's actually plus nothing minus 5. So I have to be somewhere between 170 and 175 in this thickness right here. Okay? Once I measure it, I have some number, and if all things are perfect in the world, what I'm going to measure is 60 thousandths less than the 250. So it should measure approximately 190, okay? And because I'm holding a 5 thousandths tolerance, I'd like to get this measurement within 1/1000th of an inch or so. But if I'm shooting right in here for a number that's 170 through 175, what am I going to shoot for? If this was target practice, I'm going to shoot for the bullseye. The bullseye is right in the center. So I'm going to shoot for something in the neighborhood of 172.5. We don't worry about the half, okay? Your calipers aren't going to be that good anyway. So if we measure in this 172 area, we're going to be good. If for some reason I measure right at 190, I take 172.5, that means I've got 17.5 thousandths to come off yet, right? So I take the end mill, I feed off the part, and I come up 17.5 thousandths. The likelihood that yours measures right at 190, slim to none. It's likely not going to measure that, okay? Keep that in mind. Well, if we move up 17.5, now we can do our next step, which is Z minus, and I'm going to put mine in a box, 0.0175. I put it in a box because your number is going to be different than mine, right? Once I go up 17.5, I'm going to move back in X 0.6 again. Once I move 0.6, I'm going to leave the end mill position back in here. Because the top of the end mill is going to put a radius up here on this side. Geometrically, you should see that. So we're going to take our y-axis and feed in and out, right? Once we feed in and out, we're going to position it so the end mill is on the front side of the tool, of the workpiece, so that we're conventional milling. We're going to move to the X.62 because that's what I've calculated, right? And we're going to feed across to do the finish pass right up in this region. We're going to take that last little bit of material off, just feed across. Now we're going to back the end mill away. We're going to take our dial calipers and we're going to measure. I want to measure and make sure that I lie within this 170 to 175. If I don't and I'm too thick, let me go ahead and readjust it and take another skim pass. Because when I take my end mill out, I want the thickness to be right. Okay? So at this point in the game, we've got all of the milling finished. So we've got a step on there. Okay? The last thing that we have to do is we need to put this precision hole in here. And we know it's a precision hole because on our part drawings it says 126 thousandths plus 2 minus nothing. Now I can't assume that a drill bit's going to do that, okay? We have to make sure that we use a tool that's going to give us a nice sized hole. So we want good round, good to size, and a good finish on the inside, so that when we use it in the reciprocating engine, it's a nice smooth surface for that pin to ride on. So we're going to go back to our dimensions again. Remember, we scratched out the 930 dimension and we wrote in ours. Well, we've already determined that I'm so good that I've got 930 thousandths on mine. So we're going to take 930 and subtract 813, because the only place that we have to reference is the bottom end. The top end is up inside the collet block. I cannot access it. So 930 minus 813 is 117 thousandths. So my X is 0.117. Okay, so that's my dimension. So we have to locate. Before we locate, because we did a cutting routine here, there's a burr there. So what we're going to do is we're going to take a file and we're going to deburr that corner. I want that burr gone because the burr will affect the position of this hole. Okay? We file it. We're going to put an edge finder up in the spindle. Put your drill chuck in, use your edge finder and your drill chuck. So the first step, this is the x-axis dimension, the y-axis goes in and out of the board. So we're going to say edge find your x. We're going to edge find the x. Max RPM, come in and bump off. Set our dial to 0, retract the edge finder. Once we get that far, we need to know how far we need to move, right? Here's our edge finder. Need to know how far we need to move. Number 2, X, 0.1. The radius of the edge finder is 100 thousandths. Now the center line of the spindle is even with the end of the part. Next step. X, 0.117, 117 thousandths. That's what we calculated over here. Now if I look at the top of this, there is a center position drawn out that I want this hole in the center of the piston. How do I do that? I'm going to take my edge finder. I'm going to come in on the radius, right? Here's the end of the part. It's got a flat on it, right? I'm going to come in over here and I'm going to edge find on the tangent part. Make sure that the tip of the edge finder is down below the equator of the circle. My edge find till it kicks off. So number 4, edge find. Your y-axis. Once I do my edge find on my y-axis, I'll retract the quill. Number 5, y, 0.1. 100 thousandths for the radius of the edge finder. Next step, y, 0.125. 125 thousandths, or 1/8 of an inch. Well, where do we come up with that? The diameter of the part is 250. Divide it by 2. That puts you on center. Okay? So we've got the position down. So we're actually lined up right on the center line of where the hole needs to be. Okay? Right where the center line of where the hole needs to be. So now we're going to follow the same drilling and reaming operations that we followed a couple of times previously. Right? Now we're ready to put the hole in. So step number 1, we want a center drill. Remember, max RPM, if I did my math, it still works out to be a really big number. Come down and touch it. If you touch it within 20 or 30 thousandths, I'm good. Cutting oil, this is tool steel, remember. Next step. We want to drill the hole. Well, we want to ream it ultimately. We've already decided that because the precision of the hole requires it. So if I take 126 minus the magic numbers, right, 8 to 10 thousandths, I want to be somewhere in the 116 to 118. Well, if you recall back to doing the hole in our top of our crankshaft, that offset hole, we used a drill that measured just that, 116 thousandths. And what that is a number 32 drill. If you have questions about that, go back and look at the math and go to your decimal equivalent chart and figure out which size. Remember, that 32 drill, 116 thousandths, I'm going to measure it before I drill the hole. And we're going to drill all the way through. Okay? RPM calculation. Remember, this is tool steel, so 4 times 50 is 200 divided by 0.116. Okay? Still up in the 2,000 RPM range if I round and do kind of the math in my head. So we're going to run at max RPM. Remember, these numbers that we've given you, the cutting speed and the calculations, those cutting speed numbers, as you calculate the RPM, is a good starting point. There's nobody standing above you and say, you have to run this RPM. It gives you a good starting point, okay? We've drilled all the way through. Next step, we're going to ream that hole. The diameter of the reamer is 126 thousandths. You've got another reamer that's 124. It's only 2 thousandths difference. It's less than the thickness of a sheet of paper difference. Measure it. Look at the shank. Double check, make sure you're using the right reamer. Okay? We're going to calculate our RPM for that reamer. So if we say 2,000 RPM for the drill, and it's pretty close in diameter, so I'm not going to do the math to bore you with that. But if I take 2,000 and divide by 2 or 3, right, I'm going to be in the 750 to 1,000 RPM range. Remember to reduce it. If you keep it way high, you're gonna eat up that reamer. It's not gonna work well. You get chatter inside the hole. So 750 to 1,000 RPM. Okay? Once we get that done, your piston's almost finished. The hole that we just put in, this hole right here, receives the offset pin in your crankshaft. So you're going to take your crankshaft out of your toolbox, and you're going to take that little pin, and you're going to place it down inside that hole. Number one, if it doesn't fit, you use the wrong size reamer. That's a good check. It's a good inspection check. Number two, once it sits down in, you're going to rotate that crankshaft 360 degrees and make sure it clears this step. If all your numbers are right, that step should clear, no sweat. If your numbers are wrong, you're going to have to go back in and machine more of that step there. Okay? But if you've done your due diligence on your numbers, you should be fine. So rotate it. As long as it rotates fine, go ahead and take your crankshaft out, put it back in your toolbox. While this part is in the vise and in your collet block, go ahead and deburr it with a file, emery paper, countersink for the hole, both sides, top and bottom. Okay? I'm going to take some emery cloth up around the top of the piston where I put that little step on there. I'd like it to be deburred so you're ready to rock and roll when you go to put the thing together. Okay? Once I deburr it, go ahead and put your crankshaft back in and spin it. That'll clear any of the burrs off inside the hole. All right? Once you've inspected, you're good. We're going to pop that part out of the collet block. You're going to feel it all over, make sure all the burrs are out of it. And once we get done with these lab demonstrations, you're on to your cylinder and your body. The last two components will be ready for assembly. I'll see you downstairs at the machine. We are starting lab number 10. And in the whiteboard talks that we talked about a 5C collet. So this is a standard collet that you would use on a lathe. Most machine guys would understand that this is a lathe collet. The R8 collets, which goes up inside the spindle on the milling machine, is a different size, shape, and this style collet's not going to fit up inside that hole. So if you do accidentally pick up the wrong one, you're going to see that it doesn't fit. This collet block, if I look at the shape of that collet, it's got a taper on the back side, right? Precision hole on the inside, maybe a little less than precision because students have used this and put little marks in it. But if I look inside the collet block, there's a taper on the inside of the collet block. So that means when I feed my collet into the hole, I want those two tapers to line up, right? If those two tapers line up, now when I put the nut on the back side and I pull that thread, it's pulling the collet back in, it closes up on the hole. The reason that I'm using a 3/16 collet is because my crankshaft has a 3/16 shaft on it. This is the best way that we have to hold on to small round stock like that, but still hold it good and parallel to the bottom floor and parallel to the indicated vise jaw. These collet blocks are precision ground so that the hole theoretically should be on center both in that direction and in that direction. Okay? So if I were to stand this up, try to find the center of it, I would expect that the hole is on the center of that square size. Okay? So we've already done some calculation during our whiteboard exercise that I would like to have at least my 710 thousandths of length from the face of the crankshaft back to where I'm clamping. So if I just lightly put this in here, that means that I want at least 710 thousandths from this face to where I'm clamped on, right? Where I'm clamped on right up here at the collet end. So let's go ahead and get our collet block set up. Nothing on the drawing tells me that I have to have the flat in any orientation from where the pin is, but I'm going to position it in such a way that the pin's not going to get in my way when I try to do that touch off, okay? So right now, I'm at a position where I can still move that. I'm going to put it in the vise. If you don't mind, I'm going to step here in front of you. And I'm going to set my dial calipers to 750 thousandths. So that's plenty long, and plus or minus 10. That gives me enough length that I don't run into any problems. I'm going to use the tail end, the stem of my calipers, and make sure that I have that much sticking out, okay? Now you kind of have to look at it and look at the relationship because the front of the collet's got a radius cut to it. But I'm pretty satisfied that I've got 750 thousandths sticking out. I'm going to turn my collet block around, okay? Lock my vise in. And this is a spanner wrench. So this spanner wrench has a round pin on it, and my threaded collar has round holes in it, have holes drilled in it. So if I line that up and I put torque on it, what I've done is I've applied that torque or that pressure, and it allows me to hold on to that round stock much tighter, okay? So now we're going to spin it back around so that you can see I've got enough sticking out. It's clamped plenty securely, right? I want to make sure that I have pressure applied, because if I leave it in here, it could sit in here and rock, right? I want to make sure that it sits flat down here on the ways of the vise. These are the ways of the vise. So if I put pressure down, and then I lock the vise in, if I really want to get crazy about it, I could run an indicator across the top, but I'm not that terribly worried about it, okay? So now we'll go ahead and take the drill chuck out. I need to get my dead blow hammer so that I can apply that pressure to disengage that thread. Unthread my drawbar. I'll take my drill chuck out. Okay? Let's go ahead and get my collet out. Okay, so now that I have my collet gathered up, remember this is an R8 collet because that's the one that goes up in the spindle of the milling machine. We have a 3/8 size collet because what I like to do for finding position of that slot in my crankshaft is do an edge finding operation from the front face of my crankshaft. Let's go ahead and put our collet up in. Edge finder. Remember, we're going to have to keep track of our RPM while doing this operation. I slowed down my spindle speed. I'm going to have to speed it back up so I can get up into the proper range, right? my cover back on. So now I'm going to position my edge finder down so that I can do an edge finding operation right on that front face. Forward rotation. I'm going to use this hand wheel over here, which is different than what I normally would use, just because I want to make sure you guys can see what's going on. Do an edge finding on that front face. There, kicked off. Stop the spindle. Before I move the machine, I'm going to go ahead and set this dial to 0. Or what I like to do is set it to 100 thousandths, because I'm going to move 100 thousandths just to compensate for the edge finder, so it puts me right back at 0. So I'm going to move 100 thousandths. I'm at 0, right? Which is the baseline of my dimension. We've already calculated during the whiteboard is we want to go 520 thousandths plus half of the slot width. So 520 plus 95, which gives you 615 thousandths. We'll go back over this hand wheel. 2, 4, 615 thousandths. Now I'm going to go ahead and lock my table in. So now we've moved from the face of the crankshaft to the center of the flat that we're going to machine. And now we're ready to switch tools out. I'm not worried about edge finding the y-axis because the flat goes all the way through. Okay? So there's my end mill. All of your end mills that are smaller than 3/8 are going to come through with a 3/8 shank on. So you aren't going to have to worry about switching collets around. So if we do our calculation, we're at, this is tool steel, so 4 times 50, which is 200, divided by the diameter of my end mill, which we're going to round it and say it's at 0.2, okay? Puts us at 1,000 RPM. What I'm going to do is I'm going to run at that 775 because this is a 2-flute end mill. Most of the times with cutting harder materials, I like to switch to a 4-flute. I just don't have to have one right now. But before I do my touch off, I'm going to color the top surface of that crankshaft. Okay? That's going to make me doing my touch off a lot easier. Now I want to make sure that my end mill's stuck out far enough that it's not going to hit anything in the collet system. Okay? Now 775 RPM is nothing more than switching to low range on the power switch. Okay? So now that we're at that RPM, before I put any cutting oil on it, I'm going to bring the Z-axis up, or the knee if you will, until it touches. You should be able to see some of that black Sharpie go away. Okay? Now I've got a nice shiny spot coming through. I'm going to set the dial on my knee to 0. Ultimately, I want to cut this groove 30 thousandths deep. Put a little cutting oil on it. The first step, I'm going to move down 15 thousandths. That's half the depth. I'm going to feed nice and gently across, okay? If it doesn't cut real nice, stop the spindle. There's something else going on. We fed all the way across. We're going to feed another 15 thousandths deep. So that's our 30 thousandths deep. Now we're going to back up, back through the slot. Okay. It took us a lot more time to set that thing up than it did to actually cut the part. Okay, so now I've got my flat put on. The biggest issue that I have to take care of right now is deburring it, because anytime you make a cutting operation, you can count on the fact that you're going to have some burrs. Now what I like to use to get the main part of the burrs off first is I like to take my 6-inch flat tile and just kind of roll up and over that flat. Okay? That's really all that you need to do to get that burr off, because we want our flywheel to slide real nice onto that shaft. Now I'm not putting a lot of pressure on it because I don't want to file little flats on it. It was just enough to kind of skate over that material. And now we'll take our emery cloth best we can. And I believe you can see that. There's my flat. I feel like I've done a pretty good job of that. So let's get my end mill up and out of the way. I'm going to take my collet block and put it back in the vise. The only reason for me putting it back in the vise at this point is so I can get better torque on it, okay? Trying to do this without moving the table too much. So loosen it up, loosen up that screw. Right, that nut. There's my crankshaft. There's my flat. So that part, at that stage, is completely finished. We're actually ready to assemble this. For inspection, you can take your flywheel and you can slide it down over. See how nice that slides over? As long as it slides up and down real nice over, that thing's ready to assemble. When we get to assembly, you won't have to be standing there with a piece of emery cloth and a file deburring 15 parts, okay? Those two components are finished. Next time you see me, we're going to start on that piston. Okay, we're going on to the piston. You guys recall from the lecture portion of the piston, there's an overall length that is drawn out as a dimension on that drawing, overall length of that pin. And I said to scratch that out, measure your pin, okay, and put your number in. Well, I told you during the lecture portion that I always do things just so perfect. So mine actually measures 930 thousandths. So I don't even have to change the number, okay? So 930 thousandths, the first thing that I need to determine, because we're going to go back to our 5C collets and this collet block, the first thing that we need to determine is how much do I want to stick out so that when I machine the flat on that piston, I'm not machining into Mr. Bryan's collets, right? These have been machined into a few times. That doesn't mean we want to continue to do that. We're going to take that collar, the threaded collar, and thread it up on the back side. And then we're going to do our math. You should have that math that we did already written down in your notes somewhere. It's 930 thousandths minus 310, which gives us 620. So I'm going to take my calipers. I'll set my calipers. I'm going to set them to 650. That way, it's plenty long enough sticking out that I don't have to worry about machining into my collet. Right? We're going to use the tail end, 650 thousandths. Make sure I've got enough stick out. Done with my calipers. I'm going to spin this guy around. Right? I'm going to thread that collar up on, lock it into position. Let me go ahead and crank this guy out of the way. If you recall, we said that we needed to pick a size end mill that would cut the full width of that flat all at one shot so that we're not moving side to side. I believe I told you that my preference is to use a 3/8 end mill. So we're going to take that 3/16 end mill out. Okay. I'm going to leave that same collet in there, the R8 collet, because my 3/8 end mill has a 3/8 shank on it. So I'm going to feed that up into my collet. I want to have enough stick out that I don't run into the collet block. I don't run out of travel while I'm in the middle of the cut, because that would be bad for me. Before I start coming down closer to my workpiece, I'm going to color the top surface. And I'm going to color the end, okay? We had discussed using the paper trick to reference off the end. I apologize, but what you end up having to do is get one of the other instructors to demonstrate that to you if you're interested. For the simple fact that with me missing that arm, it's hard for me to hold on to the paper and dial the hand wheel all at the same time. So I'm going to use a touch off where the machine's running and I come in and just touch the end. Now there's a couple of different senses that you can use to hear, right? You can hear the cut. You can see the cut because I colored the end, right? And you're going to be able to feel it in the machine. I can actually feel it turning the hand wheel. So what do we have to do? We have to calculate our RPM. You guys are going to be running slower than what I am because I have a carbide end mill. So we're on our top speed, so I'm going to be comfortable with that 775. We're on low range. I'm going to come back here around the back so that you can actually see on the front. And all I'm going to do is come in till I just hear and feel it touching. Okay? I can hear it just ever so faintly. Tick, 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 tick. I'm going to set my dial to 0, and that'll be my reference for the length of my cut. Now if I drop the knee back down, the advantage with doing a real nice light touch off is I didn't actually machine a feature on there. All I did was touched off. My suspicion is with a piece of emery cloth, you won't even know it was there. If I don't go too deep, I'm going to machine that material away anyway. So that Y dimension is 620 thousandths. So I've got my 0 set over here. I'm going to come up over the top surface of the part. I'm going to bring my knee down, or up, excuse me, till it just touches that top surface. There it's touched. I'm going to feed back. So now I'm going to set my knee hand dial to 0. Remember, we said that we're going to cut 30 thousandths deep, 600 thousandths back. That'd be one pass. Another 30 thousandths deep, 600 thousandths back. So let's go through that process. Let's put cutting oil on it. I've got my zeros referenced. So I'm going to feed up 30 thousandths. I'm going to come in till it just starts touching, and there's my zero. So now I'm going to feed in 600 thousandths. So 600 is 3 turns of my hand wheel. 2, 3 turns. Now normally I'd be on the other side and actually could see myself cutting the material. Because if you get to a point where you're going to run into something, you want to be able to stop, right? So I'm kind of machining blind here, but for your benefit, of course. Another 30 thousandths deep. 75 is our target dimension, so we're not even close yet. I'm going to feed in till it just starts to cut. There's my zero. There's 200. 400. 600, right? And then we're going to back off. So what we've done is we've machined down 60 thousandths of the 75 that we're targeting. Now that 75 has a tolerance on it. I'm going to blow the chips off. I'm going to take my calipers and I'm going to measure that thickness, right? I want my thickness to measure between 170 thousandths and 175. That takes into account tolerance, okay? We're going to measure that thickness. I'm going to rock it back and forth so I get a good accurate measurement. And I'm at 187 thousandths. So 187, I have to be 12 thousandths down to get to 175. And I believe we said that we were going to target 172 and a half. So 12 plus 2 and a half is 14 and a half. I'm going to feed up 14 and a half. My 14 and a half. Start my machine. Repeat that process. As soon as I start to cut, my zero should be there, right? There's 200 thousandths. 400. 600. Remember we said that that arc was going to be there, so all I'm going to do is feed front to back, okay? And because the total destination is 620, now I'm going to feed back that extra 20 thousandths on the appropriate side so that I'm conventional milling, and then I'm going to mill across. Start my machine. If I loosen the quill up, pull it up out of the way, I've lost my zero. If I change the dials or if I take the part out, I've lost my zero. So what do we think that we want to do before we change any of our setup? What I want to do is I want to measure one last time that 170 to 175 dimension. Make sure I zero my calipers. Look at that. Just a touch over 172 thousandths. I feel real good about that. Now I'm going to deburr both sides of the flat and the end of that flat. Because when I set up to do the drilled and reamed hole, any burrs on those edges is going to or could possibly affect my ability to set that position. Let's go ahead and bring the quill up out of the way. While we're close by here, I'm going to loosen the drawbar. We're going to switch to our drill chuck. Okay? I need to make sure that I have enough height because the reamer that we use has got some length to it, if you remember. So if I don't get high enough, I'm going to have some issues. I'll tighten up that drawbar. Set my edge finder in. You can see that if I'm just down in the shop making things happen, these things come together relatively quick if you have a good understanding of geometry. You don't have to be a professional machinist to understand geometry. Geometry is going to be one of those things that's going to help you out a lot as an engineer in the future. High RPM, we can double check our belt position, top set of belts, cover back on, high range, right? Bring my quill down. I'm going to edge fine the end of the part, nice and slow. I'm going to feed up on it. Out, I've edge found. I'm going to set my dial to 0. I'm going to move 100 thousandths. What I actually did is set my dial to 100 so that when I moved in I was at 0. Okay? It's a slight difference, but it does help me in saving some time. So now if you look at your part drawing that you have printed out, we're calculating our X dimension right now. Again, my part's perfect at 930, right? 930 minus 813 is 117 thousandths. So I'm going to move 117 thousandths. I'm going to lock my table into position. Now I'm going to pick up on the outside diameter of that workpiece. Right? Nice and slow. I get a good accurate edge fine. There it is. Set my dial to 100. Remember, there's 200 thousandths per rev, so if I set it to 100, I'm going to move at 100. Now I'm at 0. Now I've got to move over the radius of the part. So another 125 thousandths. Now I'm sitting in position. I'll lock my y-axis. We're going to set. We're going to put our center drill in. We're confident that we're on center. We're confident we're at the position. So now we're going to do center drill. So all I'm going to do is come down and touch it. I'm going to stop the machine. Now I'm going to come around this side and I'm going to look. I want to visually look. And I want that spot that I just put on there to be centered on the diameter. If that spot does not look or appear to be on center, you've likely done something wrong and you're going to have to go back to the edge finding operation. Okay? It's just a good visual check. So now I'm going to deepen up that center drilling, right? I deepen that up, now I'm ready to switch over to our drill bit. Again, we're going to keep measuring these things because we're too close to the end to mess things up now. Roughly 1/16, that's where we're at. That's the right drill bit. Calculate our RPM, 4 times the cutting speed divided by the diameter. We're going to drill all the way down through. Let me move that position so you can actually see what's going on. Well, these number 32 drills really cut nice. Remember, we've selected that drill bit to be 8 to 10 thousandths under my reamer diameter. What's my reamer diameter? My reamer is 126. That allows me to hit the tolerance of 126 plus 2 thousandths minus nothing. What do the reamers do? Nice precise hole, nice round hole, gives me a nice finish down inside. Put that 126 reamer in. What did I not do? I didn't check the size. Can't actually see the numbers on it if they're even there. So now I'm going to measure the diameter. There we go. We're right at 126. Get to where you're moving too fast that you forget steps. So if we divide by 3, because this is a 6 fluted reamer, I'm going to be around the 700 RPM mark. So 700 RPM is really close to that 775. So we're going to be in low range. Okay, so now nice and steady feed through. Feed back up out. While it's in the machine, I'm going to take my countersink just by hand. I'm going to spin it in that hole. So I've deburred the top side. We said that we wanted to do an inspection, not a visual or measurement inspection, but we wanted to put our crankshaft down inside the hole, and we want to spin the crankshaft 360 degrees. If the crankshaft does not clear, we're going to have to remachine that step, but this clears just fine. Okay? I feel really good about that. While it's still in the collet block, I'm going to flip it over. I'll take my file, and I'm just going to deburr that back side. Okay? Deburring the back side is going to get those sharp edges off. And because we're doing a cutting operation, we could have easily pushed a burr over, so I'm going to push that pin right back up through the hole. Clean that little edge with my single flute countersink, because it's going to clean up that edge nicer for me. Once you can run your finger across it and not get into a sharp edge, feel really good about it. Okay? So now we're going to flip it around. I'm going to loosen my collar with my spanner wrench, pull the piece out of there. My piston's done. The piston is ready for assembly. Next lap, we're going to do the cylinder, and then it'll be the body, and then we'll be ready to start assembly.